Hello and welcome. Have you ever dropped your keys or just watched a basketball make that perfect arc into the hoop? Well, that's gravity. It's this silent force that pretty much runs the entire universe, from the smallest pebble to the biggest planet. And today, we're going to break down exactly how it all works. So let's just jump right in with a question that even stumped one of the greatest minds in history.
So it all kicks off with this classic question, right? Famously sparked by an apple falling near Isaac Newton. Why did that apple just plummet straight down, but the moon, which is also being pulled by Earth's gravity, just kind of hangs out up there, circling us? I mean, it seems like a total contradiction, doesn't it? But it's actually the key to understanding, well, everything. You see, that one simple observation led Newton to this absolutely monumental discovery. He figured out a universal law of attraction that doesn't just apply to us here on Earth, but to every single object in the entire cosmos.
So what is gravitation? Well, at its core, it's a force of attraction. You can almost think of it like having a crush, where you're just kind of pulled towards someone. But here's the really crucial difference. A crush can be one-sided, right? We've all been there. Gravity, on the other hand, is always mutual. The Earth pulls on the apple for sure, but, and get this, the apple pulls back on the Earth with the exact same force. It's a cosmic two-way street.
And here it is, the law in all its glory. If you're studying physics, this is one of those lines you'll definitely want to commit to memory. It's Newton's law of universal gravitation, and it just beautifully lays out the two simple rules that govern this incredibly powerful force.
Okay, so let's break that down. The first rule is all about mass. Basically, the more massive the objects are, the stronger the gravitational pull is between them. It's a direct relationship. More mass means more force. Simple as that.
The second part, though, is about distance, and this is where gravity gets a little dramatic. The force is inversely proportional to the square of the distance, and that little word square is the absolute key. It means that as you pull two objects apart, the gravitational force doesn't just fade away gently, it absolutely plummets. So if you double the distance, the force suddenly becomes just a quarter of what it was.
So when you put it all together, you get this really elegant formula. Force equals g times the product of the masses all divided by the distance squared. But what is that g? Well, g is kind of like the secret ingredient. It's the universal gravitational constant. It's the magic number that makes the whole cosmic recipe work.
And here it is. This incredibly tiny number is one of the most important values in all of physics. As one teacher I heard cleverly put it, you can forget your crush's name, but don't you dare forget this number. It really is the constant that balances the entire gravitational equation of our universe.
Okay, so this brings us to a point where honestly a lot of people get tripped up. We've just met big G, right? The universal constant. But you've probably also heard of little g. And listen, they are not the same thing. Understanding the difference is absolutely key to mastering this whole topic.
You see, little g is the acceleration due to gravity at a specific spot, like right here on the surface of the Earth. So when you drop that apple, it speeds up as it falls, and g is just the rate of that acceleration. Here on Earth, it's about 9.8 meters per second for every second it falls.
I love this analogy for remembering the difference. Think of big G as your true friend. Always there, always reliable, the same constant value no matter where you are in the universe. Little g, on the other hand, well, it's kind of like a fake friend. Its value changes depending on where you are and what the situation is.
So why does our little fake friend G change so much? Well, for one, the Earth isn't a perfect sphere. It kind of bulges at the equator. This means you're actually a little bit farther from the center of the Earth at the equator than you are at the poles, so G is weaker there. It also gets weaker as you climb up a mountain or even as you go deep down into a mine. Its value is totally dependent on your location.
Now, this whole distinction between big G and little g leads us right into another huge point of confusion. We all use the words mass and weight like they're the same thing every single day. But in physics, nope, they are completely different concepts.
Let's really break this down. Mass is the actual amount of stuff you're made of. It's measured in kilograms, and that number never, ever changes. Weight, however, is a force. It's your mass being pulled on by local gravity, by little g. It's measured in newtons, and it changes all the time depending on where you are.
So here's the crucial takeaway.
If you went to the moon, your mass, the amount of matter in your body, would be exactly the same as it is right now. But because the moon's g is only about 1/6 of Earth's, your weight would be just a fraction of what it is here. You'd feel incredibly light, even though you are still you.
Okay, so we've spent a lot of time on gravity, this ultimate force that pulls everything down. But physics is all about balance, right? So what about the forces that push back up? Let's dive into the world of pressure and buoyancy, which are the forces that explain why a gigantic steel ship floats instead of sinking.
First up, let's talk about pressure. It's simply force divided by area. And this super simple equation has a really powerful implication. If you take the same amount of force and concentrate it onto a much smaller area, the pressure goes up dramatically.
And you see this principle literally everywhere. A sharp knife cuts easily because all that force you're applying is focused on a tiny, tiny area, creating immense pressure. A backpack with wide straps is way more comfortable because your bag's weight is spread out over a large area, which reduces the pressure on your shoulders. See, it's all about how you distribute that force.
Okay, so now let's talk about fluids, like water. When you submerge an object in a fluid, that fluid pushes back with an upward force, and we call this buoyancy. It's the reason a plastic cup pops right back to the surface when you try to push it down into a bucket of water. The water is literally pushing it up.
So whether an object sinks or floats is really just a simple battle between two forces, its own weight pulling it down and that buoyant force pushing it up. If weight wins the battle, it sinks. If buoyancy wins, it rises up. And if they're perfectly balanced, it just floats. Simple as that.
But how much buoyant force is there? Well, the ancient genius Archimedes figured this out. The upward push is exactly equal to the weight of the water that the object shoves aside. This is precisely why a massive steel ship, which is unbelievably heavy, can float. Because of its shape, it displaces an enormous volume of water, and that creates a buoyant force powerful enough to fight back against its own massive weight. So there you have it. It's pretty incredible, right? From the cosmic pull of gravity holding entire galaxies together, to the simple upward push of water that lets us sail the seas, the world is just governed by these powerful, invisible forces. The real question is, now that you know how to look for them, what other hidden bits of physics are you going to start seeing shape your everyday life?